And to end today, we're going to have a discussion. The discussion is going to be largely on spectra and timing in black hole X-ray binaries. Is the action in the corona, the jet, or both? And this is being led by PG Casella and Nick Kylafis, sorry.
Yeah, hello everyone. Thanks, Greg. And thanks to the organizers for this amazing conference. And I'm really sorry not to be there. So I think the discussion will be probably self-coordinated because I already know that many people will have several things to say, and partially these have already been going on on the Slack channel. And I think Nick has a few slides anyway to kick the discussion on with a few results and statements, right?
Okay. The subject of the discussion today is spectra and timing in black hole X-ray binaries. We have excellent models for both the spectra and the timing, in particular the time lags. However, nature sometimes can be nasty to us. And what nature did this time is that it correlated the spectra and the time lags in black hole X-ray binaries. So that makes it much harder for models to explain. Easy to explain each one, but the correlation is a bit harder. So that's one question that I will come back at the end. Let me show you some data first. Pablo Reg analyzed the data from GX339-4 and found this nice correlation. Ignore the blue dots for the moment and concentrate on the x's. The black x's at the bottom left are from the bottom part of the hard state, from the hard state. The red x's are from the upper part of the hard state. I'm talking about the Q diagram, which is a vertical line for the hard state, and the green crosses are the hard intermediates, are from the hard intermediate state. So this is a stringent correlation that the models have to address. Some of you may say, GX339-4 is a peculiar source. Why should we pay attention to it? Well, Pablo looked at 13 of these sources, so all the data that you could find, plotted them here, and he concluded mathematically that there is a correlation. I'm not happy with it. I'm sure you're not happy either. It looks like a scatter diagram to me. But if you ask the right question, then interesting things come out. If you ask, let's separate the low inclination sources from the high inclination sources, just to see what we get. And you get two nice correlations. The black dots are for low inclination sources, and the red dots are for high inclination sources. So all this scatter that you saw before is due to inclination. And Pablo, in a paper that we published together in 2019, separated them in three categories: low, intermediate, and hard. And lo and behold, they make three lines, more or less, with the intermediate in between the other two. So the correlation is there. And it is inclination dependent. So it's another constraint. Now, Altamirano and Mendez found that the phase lags are correlated with the cutoff energy of the power law spectrum. So it's not only the spectral index, but also the cutoff. the high energy cutoff that correlates with the time lags. So the entire spectrum, the hard X-ray spectrum, correlates with the time lags. So here are the questions that Pier Giorgio and I give to you. Do the time lags produced by all current models correlate with the produced spectra? Let me go through all of them, and then we'll come back and discuss each one of them. This is my last slide. Which are the main problems for current models? Are there any showstoppers? Do we need both a corona and an outflow to explain the reflection spectra? Can the outflow replace the lamppost? Are X-rays alone sufficient to eliminate degeneracies? Now, many questions, and that's it regarding my introduction. So I want to ask the first question. The current models address this correlation between time lags and spectrum?
So let's see if there are any raised hands. I don't see any. Are there any in the room? Yeah, Phil, here.
Can you hear me? Yeah. So Pierre is speaking. So concerning the JETSAD model, for sure, for example, we do not take into account the timing properties.
Can you take your mask off,
yes,
please?
Sorry.
Yeah.
So concerning the JETSAD model, for example, for the moment, we do not take at all the timing properties.
Mm-hmm.
So for sure, it's already tough actually to take into account the spectral evolution. And of course, this is the objective is to take into account the timing, but for sure, this is not yet, we do not yet have constraints on the timing. It's tough, but I agree with, so just to answer, JETSAD model is one of the models that try to explain the spectral shape, but for the moment, we do not explain the timing properties.
Okay. Also, I communicated by email with Phil Attlee, who has been working in explaining this correlation together with Julien Malzac. And he told me he has a poster, which I haven't seen, but maybe Phil can intervene and say what he wants to say. I would love to.
I'll keep it maybe generic a bit instead of too model specific, because obviously, you can go and have a look at my poster as well. I think that the first thing to bear in mind, of course, with gamma is just thinking of the origin of gamma, right? It comes from the energy balance in the corona between the seed photons and the heating, right? So this is just a general point. And I think everyone probably agrees that, most people will agree, I think, that the seed photons come from the disk in the brighter hard states, right? Which is the lags that we're talking about. But of course, the fainter hard states, there's also evidence that you get the synchrotron emission that can also contribute. So you get this change in the kind of global correlation of gamma and accretion rate, for example. So obviously there's changes in coronal geometry, and we see these changes in the strength of the disk compared to the power law emission. So that suggests a change in the balance of the heating to the seed photons. So sort of that's, you know that you have to have some sort of geometrical change. And so any lag model would have to have some dependence on that geometry to get those relations, right? And so that's where I think, that this thing sort of fits in the picture that you're trying to explain. If you have lags generated either by reverberation or by the response of the corona to variations going inwards or anything like that, then you can do that in principle if you have a bigger corona. So we heard, for example, in Jingyi Wang's talk about the interpretation of the lags getting larger is that the corona gets bigger. So if a corona gets bigger vertically, then you would end up with a softer spectrum, so you get that correlation. So we can also get that in the model I talk about, where we talk about those lags not as being light travel, but due to propagation. But so that's the kind of thing you want to explain. And I think the interesting questions then, okay, so that's a general point about geometry. are more like the details. Like, well, I think the point you made, Nick, about the inclination dependence is very interesting. We see that also in the QPOs. That's something I haven't really thought about. And also, when you see these lags, Mike Novak pointed out years ago that when you plot this lag versus frequency, we know that the lags depend on frequency and it drops, but it also has these steps that you see in the profile, and the steps seem to correspond roughly with the Lorentzian components that you see in the power spectrum, so maybe suggest different components contributing on different timescales. So there's a lot of complexity there that I think we need to address as well in the shape, the frequency dependence of the lags, and not only on the broad correlations. And we need to look at geometry changes. And I think most models can do that in different ways, but none of them have really, we've not yet got to the point of competing models, right? So we've got to the point of trying to fit them to the data, but not actually testing one versus the other. And of course, we have to do hypothesis testing if we're really going to tell the difference. So that's without pinning down onto one model, that's my general sort of take on the lags, that we're getting there because we're building models, but we need to consider much more than the correlations of different parameters, but also actually detailed spectral timing fitting of lag versus energy, and the energy, all these kinds of things that we get from the data. So that's my point, I guess.
Yeah, thanks, Phil. Yeah, I agree. I think this goes in the same direction as Rob Fender comments. The difference between the Xraybinary and the GRB community is that we are lagging behind, and we need more models, more dedicated models. Here in Zoom, there is Gullo who has raised his hand. So Gullo, I think you can go ahead.
Yeah, just like a quick comment on the reverberation lags. Even if I don't know if the terminology is anymore correct, but there is like the dilution effects that affects these reverberation lags. So this dilution is basically when the energy band that you are considering is not dominated by just one component, but is a contribution of both the continuum emission and the reflected emission. So if the energy spectrum changes, then you have changes in the lag due to just dilution effects. So this is not like the hard lags, but in terms of like reverberation, of course, we have correlation between the energy spectrum and the lag that we observe just due to the dilution.
Thanks, Gullo. Anyone else? Nick, is that okay? I see someone stepping up in the room.
Hi, this is Alexandra Veleda. So I was going to point also to the important part, which is the spectral evolution. So when you, for example, consider your propagating model, or like propagating fluctuation model, then you need to also take into account that your spectrum changes, so the spectral shape changes, and these also can contribute to the lags. So this is one thing, but then another thing, if you, for example, as Phil, for example, also agrees that we at some point have synchrotron and then at some point have disk comptonization, then somewhere in between we should have these two. And having two continuum components would also change and mix up the time lags which we observe. So, I mean, when we consider the lags, we should also take into account the energy and the time range which we are looking at. So this can be like, I mean, for different sources, this the interplay of the different components can contribute a lot to the difference in the logs.
Thank you, Alexandra. Can I say something, Greg?
Yeah, Nick, go ahead.
Okay. I can understand why time lags caused by comptonization were rejected 20 years ago. The original suggestion was by Hua, Kazanas, and Titarchuk or some permutation of these names, was that they invoked a huge corona, 10 to the 10 centimeters, to get 1 second time lags. And the response of the community was, this huge corona, how can you keep it hot out to 10 to the 10 centimeters? So then people abandoned the hot corona and hot and large corona. However, if you have a small corona and an outflow, then you have a larger corona. In other words, if your comptonization region is both the hot corona that everybody takes for their comptonization plus the outflow, then you can explain, as we have, these correlations very nicely, and the inclination dependence, the time lags versus cutoff energy versus gamma, and all that. So, and I don't understand why people do not want to make this little step where they're here. This is the corona, and the next step is to include in it the outflow. This has been done years ago by Sarah Markov, who pointed out that comptonization at the bottom of the jet may play a significant role. And I think indeed it does. Comptonization, in my opinion, is preferable for the following reason. The same mechanism produces both the spectrum and the time lags. The hard photons come later than the softer photons. So if the same mechanism produces both, then it's kind of natural that the two will be correlated. If you have two separate mechanisms, they can conspire to produce a correlation, I'm sure, but it's more difficult. So I'm not telling you that the comptonization is the mechanism, but don't ignore it. It may play a role. So I'm willing to see Phil's and Julian's paper on propagating fluctuations and correlation with the spectrum. Fine, yes. Different models will help us sharpen our thinking. The second question is, which are the main problems for current models? There are any showstoppers? No showstoppers. Yes.
So
at the moment, the comptonization model may have an edge, but it's because people have not tried to find correlations with the other models, and they should try.
So Nick, Phil has his hand up.
Yeah, exactly.
Yes, so actually, yeah, in terms of, I think, showstoppers or general problems, I'll talk about in the propagation models. I think one of the issues that comes up, and all the different models for propagation have this. So Chris Stone and Rad Mahmoud's model has the same thing, and so does the one in my poster. You end up for propagation requiring really quite short propagation timescales, and this was also alluded to earlier today as well. But I think this is a real issue, because what we see when we look at now we have soft X-ray data, so we have nicer data and also previous XMM Newton data, and you can clearly see the disk black body in the hard state varying, and that it leads the power law variations by tenths of a second or something like that on tens of second timescales. But that's really fast for a disk, for a thin disk. But if it's a black body, can it really be? Well, it can't be a hot flow, right? But it's probably not geometrically thick at those accretion rates. So I think that this is telling us that maybe we're missing something in the variability of these accretion disks, at least from the classical ideas of viscous timescales. And so I'm really excited actually to hear all the work being done by the GRMHD people, looking at finding these effectively faster propagation for these magnetically arrested disks, for example. And so I think, you know, my hope is we're at a point where at least we can sort of confront those particular propagation aspects with the simulations finally, and maybe, you know, talk to one another and make some progress. So it's sort of not quite a showstopper, but it could be, you know, in the end, if the GRMHD simulations get sufficiently, you know, advanced, that we can really compare with these systems in detail.
So if I can make a step backward, I think there are now many evidence discussed by also in this conference about the possibility that the disk extend all the way down, or almost all the way down, or anyway that the corona is compact and possibly vertically extended. So I think when we discuss whether we need both a corona and an outflow, whether they can both be active and play a crucial role, the question comes to me about what is the actual difference in between a vertical corona and the base of the jet. And I see that this has been already started as a discussion on the Slack channel, and there have been already several interesting inputs. But I think there is still room for clarifying the issue here. In particular, I noted a comment by Sarah mentioning the fact that many simulation show a mixed contribution of inflowing and outflowing matter in the same component, if I understand correctly. So if Sarah feels like commenting further on this, or anyone else, about what is the actual difference we can use in the model in between at the base of the jet and the vertical corona. I know there is also a terminology issue about what is the jet, whether it's a pre or post the acceleration, and whether it's a pre or post the jet collimation or particle acceleration. But I think, of course, this goes beyond the actual terminology, right?
Yeah, I mean, I think we can't really answer this yet. You know, I was going to bring this up on the discussion Friday, but you stole this. But I think, you know, the problem is that we're really in the early days of the kinds of simulations that I think need to sort a lot of this out. I mean, you heard from the talk just a little bit earlier from Navin, and then of course, you know, Matthew and so on, like the state of the art of what's going on. And the problem is that you really need to include the radiation self-consistently, which is going to affect the dynamics in a lot of situations and so on. But I mean, if you just take the basic ideal MHD simulations, you end up with nothing that looks like the old cartoons, right? I mean, the old cartoons, whether it's, you know, the corona is like sitting on top of some thin disk or a little ball or something like that. I mean, you don't have static regions. I think we all probably agree by now that the magnetic fields, I think Jonathan is going to talk about this, is it tomorrow, but the magnetic fields seem to be just threading this region. You can't get rid of it for many reasons. It might even help the timing problem, as Phil was saying. But once you have these strong magnetic fields and you have ionized plasma, you're going to end up with motion, right? So I think we can get rid of static coronas probably pretty well. And then the question is, which way is it moving? And it's probably a interface region, is my guess. It's probably a little bit of both. I mean, in the simulations, you see a kind of interface wind, some people call it a sheath, you know, between the jet funnel and the accretion disk. And I think that would be my best guess as sort of where you're going to end up with the corona. But Matthew in his talk was speaking about this kind of squashed region underneath them, between the different sides of the jet in the MAD region. And so probably we're not going to be able to start really making this mapping until we have slightly better simulations. But I think in the end, I'm not sure. I mean, if you think phenomenologically, the more better data we have, the better chance we have of answering this, I think, in terms of do we need one or two zones, right? Because there's many models you're hearing about where we need either two reflection components or we need two different spectral components. And I guess I think the jet, in the simple case, I would always say, and even though I know I was the one who first suggested it, I think the base of the jet being the corona, I think it's not quite that simple. That's what I would say.
Okay, I would like to ask you what you mean by better data, but I think I can give the floor to other questions.
Yeah, I don't want to keep rambling. Sorry.
Yeah.
Well, I was just going to make a very quick point, and that was that when it comes time to trying to get the better data, we're in this catch-22 where oftentimes they're asking us for the simulations that we're testing. And so, of course, I mean, Sarah knows this well, but just a reminder that it's really important for all the observers and the theorists to really be working together to drive each other's research even further. I know it's sort of obvious, but.
Yeah. Okay. So I see there is Pop standing since a few minutes already, and then there is another hand raised on Zoom.
Yes, to answer to your comment, Pier Giorgio, about if we can, what is important from the place of the corona, if it is in the disk or an outflow. I think that the main constraint is coming from the optical depth. When you feed the data, the optical depth is of the order of a few. And I think that at least from accretion ejection models, it's quite difficult to have this type of optical depth in the outflow, because the density is decreasing very rapidly as soon as you increase above the disk. So I think that it suggests that most of the computerization is produced where the matter is, so in the disk instead of in the jet, I would say. This is my main point of view.
Doesn't this depend on the level of...
I know that Nick does not agree on that, but this is my feeling.
We need, if it is done in the disk, then we need to explain the inclination dependence of these correlations. So
for sure, there is an inclination dependence.
Yes,
if you have a corona also, I mean, of course. But I agree, this has to be taken into account.
If in addition to the disk, one has an outflow, then the symmetry is broken and you have a cylinder on top of the disk, and that creates anisotropic spectra. Along the cylinder, you get the hardest spectra because they have this photon scatter them most times, and perpendicular to it, the spectrum is much softer. So the outflow helps to explain the inclination dependence.
No, but for sure, in the corona, you have exactly the same thing. I mean, the optical depth vertically is not the same as the one radially, so you will have the same type of effect. But this has to be tested, I agree, but there is a dependency on the inclination for sure.
There's a question from there.
And there is another comment here.
Hi, this is Thomas Strauser. I have a comment. I mean, this now kind of is a very theoretical discussion we're doing, but I feel like the problem is a little bit more fundamental. We're just beginning to bring spectra and timing kind of together, and even the simple models, it's already really hard to fit the data. And I think that's one very important thing. And we've started looking into this the last year, so different groups have, where this should not be overlooked. We're seeing the same phenomenon, timing and in spectra. And clearly we can talk about inclination dependence and so on, but then you can also have to calculate what does this mean then for the spectrum and not just for the timing, because it always predicts both. So we kind of need at least more basic models maybe to explain these things.
Yeah, exactly. Yes, thanks. So Navin,
I just want to point out that we are technically at the end of the session. There are 2 more comments. If people are okay with going a teeny bit over, I suggest we let Navin and Jonathan make their comments, please.
Thank you. I just would like to add one more point to what Sarah mentioned, that we can definitely disregard the static corona ones, because when you add in field lines and then if there are charge particles, there's definitely going to be some motions associated with it. So in our picture of the whole chain comptonization that I just talked about, the outflows are not aligned to a very small opening angle, for example. So they are they can be a bit more erratic. They're definitely not aligned along the equatorial plane of the disk, because these reconnection events are coming due to the colloidal field lines reconnecting in some sense. So they are definitely going outside of the black hole and also can be towards the black hole, but the opening angles can be quite broad. That's one point. So the other point is that as far as the expansion and the height of the lamppost is concerned, as an outburst evolves, as the flux increases, what you would also expect is that more and more magnetic field lines are affected along with the disk, and a stronger field line accumulated near the inner edges of the disk can give rise to a longer or taller reconnection regions or the reconnection layers from where the containerization happens. So, and this could possibly be what we are interpreting as changes in the height of the lamppost. Yeah, I'll leave it there. Thank you.
Yeah, thanks, Nick. Jonathan, you want to say your point?
Yeah, it's also a comment related to the jet, and Nick was saying that take the picture of a cylindrical jet, and of course we have to start with simple pictures always. But there's no such a thing as a cylindrical jet. In asymptotic regime, of course, yes, probably, hopefully. But if you want to start right from the beginning, let's say from the accretion disk, you need a huge pressure and indeed a huge density, which might be possible if you have like in the old pictures where you have a lot of material. And why not? But I'm not sure this will be consistent with the opacity, or otherwise you will have something which will be like centrifugally driven and which will open dramatically and the density falls down very rapidly. So I'm not sure where exactly you may have like almost a constant density so that you have the correct opacity. So this is a real problem. And I would suggest maybe to put numbers and to try to relate if the density and the way the density which is required to explain the quantization and what is observed is consistent with what we know from jet acceleration. That's it.
If I may respond in 1 second, the cylinder that I mentioned was just a schematic. In our calculations, we assume a parabolic outflow. And yes, the density does decrease. And yes, the scattering happens near the bottom and a bit further up, but not very high up. Yes, this is all agreed.
Okay, so Greg, what do you say as a chair? Shall we keep discussing until midnight, or we call it?
I think it's time to thankfully to thank everyone for their contributions to the discussion and close the discussion and hope everyone has a wonderful day. I don't know if there are any comments from the LOC, but I'll let the recording stop.